The research proposes a novel consensus-based distributed variational multi-object tracker for multi-sensor networks, addressing the challenges of accurate and reliable tracking systems in cluttered environments. It begins with a centralized sensor fusion scheme, where sensor data is transmitted to a fusion center, and then develops a distributed version leveraging the average consensus algorithm. This distributed approach requires only local message passing with neighboring sensors, making it theoretically equivalent to the centralized sensor fusion tracker. The authors highlight the limitations of existing distributed data fusion methods, which often rely on specific network topologies and come with high computational burdens. They discuss approximate methods, such as geometric average fusion and arithmetic average fusion, which are suboptimal and can result in degraded tracking performance. The proposed solution leverages the non-homogeneous Poisson process, NHPP, measurement model and recently developed NHPP trackers. The authors extend the variational Bayes multi-object tracker presented in previous work to multi-sensor cases, achieving superior tracking performance in terms of accuracy and implementation efficiency. The key contribution of this paper is the development of a variational filtering framework for tracking multiple objects in a distributed sensor network using the average consensus algorithm. Each sensor in the network runs locally using its own measurements while communicating with neighboring sensors to obtain global statistics for the local coordinate ascent update. Once the average consensus algorithm converges, the local estimates for each sensor are updated using the global statistics obtained. This approach enables the distributed version to perform on par with the centralized version in terms of tracking accuracy, while reducing communication costs and increasing robustness against single-node faults. Simulation results show that the proposed distributed multi-target tracker outperforms the suboptimal distributed sensor fusion strategy that fuses each sensor's posterior based on arithmetic sensor fusion and an average consensus strategy. The proposed distributed variational tracker outperforms the arithmetic fusion method in terms of tracking accuracy and efficiency. It enables distributed sensor fusion and tracking without requiring complete knowledge of the network topology, making it more efficient in communication costs. The problem formulation involves tracking multiple targets in clutter under a distributed sensor network with time-varying communication links. The joint state of the targets at each discrete time step is represented by xn, which is a concatenation of the kinematic states of each target. The sensor network is modeled as a graph G, T, with a set of sensors S and edges E, T, representing the communication links between sensors. The measurements received from all sensors at time step n are denoted by yn, which includes measurements acquired by each sensor. The dynamical model assumes that targets move in a 2D surveillance area with an independent linear Gaussian transition density for each target states. The NHPP measurement model and association prior are used to model the measurement process. The NHPP model assumes that each sensor independently detects targets, and the total measurement process is a superposition of the conditional independent NHPP measurement processes from K targets and clutter. The associations of all measurements yn are denoted by theta n, which represents the origin of each measurement. In this section, the authors present a centralized sensor fusion framework for tracking multiple objects in clutter, using a coordinate ascent variational filtering algorithm. The objective is to estimate the posterior distribution p, xn, theta n, y1, n, given observations y1, n from all sensors in the network. To address the intractability of the exact optimal filtering recursion, the authors replace p, xn-1, y1, n-1, with a tractable approximate filtering prior, which corresponds to the converged variational distribution q** operator n-1, xn-1, obtained from the previous time steps approximate filtering. The authors assume a mean field family of variational distributions that satisfy the factorization qn, xn, theta n, equals qn, xn, qn, theta n. They then iteratively update qn, xn, and qn, theta n, until convergence is achieved, resulting in the converged variational distribution q** operator n, xn, theta n, that approximates the target distribution Pn, xn, theta n, yn. The update for qn, xn, involves using k pseudo-measurements ykn, k equals 1, 2, k, which can be considered as updating the predictive prior pn, xn, with these pseudo-measurements. Given an independent initial Gaussian prior p, x0, and the transition model in 1, the updated variational distribution can always be in an independent Gaussian form, i.e., qn, xn, equals n airy product kk equals 1 quadrillion, xn, k. The update for qn, theta n, is performed by individually evaluating qn, theta sn, for each sensor, where the update can be carried out in parallel. Each qn, theta sn, j, is a categorical distribution, and the updates for theta n can be independently carried out for each theta n, j. The authors also discuss the initialization strategy, adopting the method in 10, where the algorithm starts the recursive updates from qn, xn, and the initial variational distribution q, 0, n, theta sn, for each sensor s. The initial variational distribution q, 0, n, theta sn, is a categorical distribution with probabilities proportional to the likelihood of the measurement originating from each object or clutter. The consensus-based distributed variational multi-object tracker algorithm, outlined in Algorithm 1, takes as input the previous time steps variational distribution, the current measurements, and the maximum number of iterations. At each sensor, the algorithm initializes the variational distribution and performs a series of updates using Kalman filtering and distributed average consensus. This is achieved by iteratively updating the state of each sensor node using its own state and the states of its instantaneous neighbors, employing the metropolis weight to compute the linear weights in equation 18. Once the converged values of omega s, k, 1 and omega s, k, 2 are obtained, the required pseudo-measurements yk, n and rk, n can be computed using equation 19. The algorithm then updates the variational distribution qn, xn, locally at each sensor based on the centralized pseudo-measurements calculated at all sensors using the distributed consensus algorithm. The overall distributed implementation of the variational tracker is summarized in Algorithm 1. The performance of the distributed tracker is compared with the centralized and optimal distributed fusion methods in the results section. The simulated dataset consists of 20 sensors observing 50 targets in the surveillance area, with a total of 50 time steps and a time interval of 1 second between observations. The parameters of the constant velocity model are set to sigma k equals 5 and rs, k equals 100I, where I is a 2D identity matrix. The target Poisson rates are set to 1, and the clutter rate is 100. The robustness of the algorithm is evaluated by generating multiple datasets with varying levels of noise and sensor failures. The paper introduces a novel optimal distributed variational multi-target tracker for sensor networks, requiring only communication between neighboring sensors. This method achieves equivalent tracking performance to centralized fusion while maintaining a decentralized processing architecture and reducing communication costs. The simulation results demonstrate the equivalence of the proposed optimal distributed fusion and the centralized fusion in terms of tracking accuracy. Distributed multi-target multi-sensor tracking is crucial due to its challenges and the need for robust algorithms. Various distributed estimation techniques are reviewed, including arithmetic and geometric fusion of beliefs, consensus problems in networks of agents with switching topology and time delays, and fast linear iterations for distributed averaging. Previous work on distributed particle PhD filters using arithmetic average fusion of Gaussian mixture parameters, likelihood consensus, and its application to distributed particle filtering is also discussed. The proposed optimal distributed variational multi-target tracker utilizes a non-homogeneous Poisson process for modeling the target and clutter measurements. It uses a variational Bayes approach for data association and multi-target tracking, allowing it to scale well with the number of targets and sensors. The algorithm operates in a decentralized manner, with each sensor node estimating the target states using local measurements and information from neighboring nodes. The authors employ the average consensus algorithm to achieve consensus among sensor nodes on the estimated target states. The performance of the proposed tracker is evaluated through simulations, comparing it against suboptimal AW distributed fusion and centralized variational multi-target tracking. The results show that the proposed optimal distributed fusion outperforms the suboptimal AW fusion in terms of mean OSPA metric, and converges to the centralized fusion's performance within approximately 10 iterations of the average consensus algorithm. Future work includes extending the current distributed variational tracker to handle unknown target numbers and heterogeneous sensor networks with varying coverage. The research is sponsored by the U.S. Army Research Laboratory and the UK Maud University Defence Research Collaboration, UDRC, in signal processing.